is Julita Corbalan from the Barcelona Supercomputing Center, and I'm going to present you the energy optimization and analysis with the EARL management framework. So this paper or this work is going to be presented in the context of the Energy Efficiency HPC State of the Practice 2020 workshop. EARL is an energy management project resulting from a BSc and Lenovo project started in 2016. So it's operational since August 2019 at a set on SuperMUC-NG in more than 6,000 nodes. This software is open source under the license BSD3 for individual non-commercial use and EPL 1.0 license for commercial use. So I think there is no need to explain you why energy is important, but just really quickly, energies are really expensive resources. It's a limited resources that need to be managed efficiently, and the problem is that it's difficult to manage, involving many aspects in a system, from the hardware, the application, the cooling system, the global monitoring, etc. The objectives of the EARL project are to provide us a global management system that provides an easy, transparent, and powerful way to manage the energy. And concerning the optimization in particular, we want to provide a solution at runtime. Okay, so that paper is about that. In general, EARL needs to be flexible and configurable, so that you will see we provide energy policies, models, monitorings, everything like plugins. Okay, so here in the picture you can see the four main EARL components. So the runtime library is the component I'm going to talk about in that paper, and it applies at the application level. The runtime library provides energy control, accounting, and optimization. The node daemon or EARL daemon is the component running in compute nodes. There is one daemon per compute node, and it offers job monitoring, accounting, control, and it provides also the support for some privileged metrics. The database manager is the component that reports all the information collected to the database. There are, or it could be multiple database managers in an installation. Okay, so you can have one or many depending on the system size. And the global manager is a component providing global monitoring and energy control at the cluster level. So summarizing, in the core of EARL, there is a powerful monitoring system. Using this information collected by these components, we provide energy accounting for all the jobs in the system. All that information is reported to a SQL database, and it's associated with the job ID, step ID of the scheduler. In that case, we offer EARL for Slurm. This information can be used also for a later application analysis, but the most important thing is that all this information that are collected at runtime are the one used for application optimization. In particular, the EARL library offers energy optimization for MPI applications. So let's go to see the details of the EARL library concerning energy optimization. So the problem of the energy management is that the energy depends on power and time, and this is really dynamic. It depends on the application, if it's more, let's say, CPU intensive or memory intensive. So in the picture you can see two examples. The one in the top is a CPU intensive application, so you can see the power, performance penalty, and energy savings are totally different from the one on the bottom, which is a memory intensive application. It not only depends on the applications, it depends on the hardware, it depends on the other applications running at the same moment, the temperature of the system, the inputs of the application, the specific nodes. So of course all these things give us to the conclusion that it needs to be a runtime approach. Not only EARL, of course, is doing a runtime approach, there are many other solutions. So the EARL library provides optimization at this moment only for MPI applications. We are working in the next releases to provide other use cases. So Intel and OpenMPI are supported. So the really interesting thing is that not source code or user input is needed at all. The current version is for Intel CPUs, And the way we are doing totally transparently is because the EARL library is loaded using an EARL Slurm Spank plugin. Okay, so this kind of plugin, this kind of Slurm plugins are a very nice solution because it allows us to be totally integrated in the submission system. So for instance, in a system with EARL installed, you can run sbatch -h, osrun, osalloc, and you will see the different EARL options for job submission. Okay, so of course EARL has default options for everything, but these options are available in case you want to change something that is not the default behavior. So these are the main steps for job submission with EARL using the Slurm Spank plugin. So this is a technical detail. Okay, so when you do an batch of a job, there is a local part, where local part means the submission node, where some of the options are initially validated. In a second stage, there is a part of the plugin executed in the context of the step of the application. That part is executed remotely. Remotely means compute node. So this remote part is the one that connects with the EARL daemon, notifying the EARL daemon there is a new job. So the new job sends the application identification and the submission details like the policy settings, CPU frequency in case the application has selected something specifically, etc. So some of these options are only available to EARL privileged users, or the EARL daemon validates by checking with the EARL configuration file, which is a simple text file, these options are correct. If there is nothing specific, the EARL daemon will apply or will notify the submission plugin the default options must be applied. Okay, and this is a per job configuration. Once the Slurm plugin receives the validation, the answer from the EARL daemon, in a last stage, the plugin configures the LD preload environment variable to set the lib EARL as part of the library that needs to be loaded automatically. Okay. So when the EARL library is loaded, it starts what we call the EARL library lifecycle. So the internal behavior of the library is an iterative behavior. So it starts by an MPI call interception. So the EARL library intercepts all the MPI calls. So the library itself is started with the LD preload, but the MPI call are, let's say, intercepted using the PMPI profiling MPI standard mechanism. Okay, so in the case of the EARL library, it is potentially compatible with other profiling libraries using the same approach, since we identify the list of symbols that are needed, that needs to be called after the EARL library. Okay, so the EARL library automatically converts each MPI call in a dynamic event that are the inputs for our loop detection algorithm. We call it denies, and we will see just few details in the next slide. Okay, so this denies algorithm is able to identify dynamically loops, even nested loops in the application. So the idea or the target of denies is to provide the other loop of the application to the EARL library, and it drives the behavior of the library. So once the loop is detected and several iterations are executed, where several iterations depends on the mechanism to measure the energy, it could be 1 second or 10 seconds. Okay, we identify that automatically. We compute the application signature. Application signature is a kind of electronic signature of the application with a set of metrics that clearly characterize what the application is doing at that moment. So there is no need of inputs, information for historic databases. There is no need for anything. It's totally on the fly. The application signature is part of the computation of the energy models. Energy models depends on the hardware, and once the energy models are applied and we have projections for time and power for all the CPU frequencies, we apply the energy policies. Okay, so the energy policy selects the CPU frequency, and this internal loop of the EARL library is executed again in case a new signature, that is a change on the application behavior of a new loop, is detected. Okay, so even though the denies algorithm is really optimized, there is an internal mechanism to estimate the overhead, because the main source of overhead for EARL library is this loop identification, that switch denies on and off dynamically depending on that overhead estimation. Okay. So just a summary, what's denies? So the idea of denies is to identify automatically repetitive patterns, that in our case means loops. So for instance, in the picture you can see a very simplified, of course that's not really synthetic, of a potential sequence of events. Okay. So at that point, when we see this 1, 3, 2 repetitive pattern, okay, denies identifies a sequence, and when it appears again 1, 3, 2, denies it reports to the library that we have a new loop. New loop is one of the specific denies events. Okay, so after that, every time it appears the 1, denies will notify there is a new iteration. So this is a new iteration, 1, 3, 2, 1, 3, 2, new iteration again and again. Okay, and when there is an event that breaks the loop, an end loop event is reported to the library, and then starting again the process of computing application signature and so on. Okay. So in order to be really efficient, the Aneas is internally implemented as a recursive algorithm, where the algorithm that is really optimized is the basic one. Okay, so it's highly optimized for Intel architectures using AVX2 and AVX512 instructions. So the applications and system signatures are the inputs for the energy models. So the application signature depends on the application and is computed at runtime, and here you can see some of the metrics used in the current models. So CPI, that is cycles per instructions, TPI, which is main memory transactions per instructions, the DC node power, the iteration time, and the percentage of AVX 512 instructions, which is really relevant for Intel architectures. Okay, the system signature characterizes the hardware itself. Okay, and it reflects the hardware characteristics regarding power and performance through an energy model. Okay, so the whole picture is like that. So once we have the application signature computed at runtime, the system signature is computed at EARL installation. Okay, we are ready to compute or to apply the energy models, and energy models. So you can see in the picture the basic energy models EARL includes. Okay, generates time and power projections for all the CPU frequencies. These time and power projections, together with the specific policy configurations and the current application state, where application state means if we are still computing the application signature, if it's the first time, I mean, it's not nothing related with the application, it's related with the internal EARL library state diagram. We select the CPU frequency dynamically. So the energy policies in EARL, there could be multiple energy policies installed, but only one energy policy is applied per application. So in particular, EARL includes three energy policies: mean time to solution, mean energy to solution, and the third one, monitoring, is not really an energy policy, it's just a policy for application monitoring, really practical for application analysis. In that case, the application runs at a fixed frequency. Okay, so these energy policies are available through plugins, so there is no need to reinstall EARL in case a new policy wants to be enabled in the system. So that paper has presented the evaluation of a set of applications when using mean time to solution. Mean time to solution is the default policy at SuperMUKG at LRZ for MPI applications. The target of mean time to solution is to boost applications that presents a good performance scalability compared with the frequency scalability. So what we compute is what is the speed up or the acceleration when increasing the frequency compared with the ratio in this frequency increment. Okay, so the policy accepts what we call a policy frequency that reflects the minimum gain to check the next CPU frequency and the next one and so on, because we check between the default one, which is default frequency, which is lower than the nominal. Typically it's 4-5 p-states less, up to the maximum. So for instance, in the paper, we have executed our applications in a system where the maximum frequency is 2.4 gigahertz, and we have selected the default frequency of 2.0 gigahertz. Okay. Because one of the nice things of EARL is that given the EARL is not only a runtime, given that the EARL library is one of the components of the EARL framework, the application analysis is really nice integrated in the whole system, and it's really easy for application analysis, okay, application monitoring, and to check, to evaluate the benefits provided by the EARL library. Okay, so EARL provides job accounting for all the jobs, not only MPI. And all the metrics are reported to an SQL database. So that means that information can be later collected doing directly queries to the database, showing the information in some visualization tool like Grafana, for instance. But of course, EARL provides some tools, some EARL tools to automatically report or to automatically gather the information that is more, let's say, more relevant or more typical for application analysis and for system analysis. Okay, so all the components in EARL contributes to have a global view of the system in terms of monitoring. So the EARL library, for instance, contributes with the application and loop signatures, because the loop signatures or the application loop signatures computed at runtime are reported to the database. EARL daemon contributes with what we call a basic application signature, that is the application ID's information, like the job ID, step ID, user ID, application name, etc., and time and power, which is the basic ones for energy analysis, and node monitoring. The ERDVD and the EARL Global Manager, which are not included in the paper, for instance, the ERDVD contributes with aggregated node power per groups of nodes, okay, and the EARL Global Manager contributes with cluster monitoring. So there are two commands to gather information from the database, and in that paper I will present you very briefly the e-account for job accounting. The e-report is in charge to provide reports, energy reports about nodes, system, users, and so on. Okay. So one of the important things I have already mentioned is that since EARL uses the same IDs than the scheduling, in that case SLARM, it's really easy to use. Okay. There is also some other options not presented here, like for instance generating, when the application finishes, some CSV file with all the metrics, all the performance counters details the library collects during the execution. So the scheme for the job accounting is something like that. Every n compute node sends the information to the database through one ERDVD, okay, and then the different ERDVDs send the information to the DB server. So for instance, if you submit a job and you get the ID 142727, you can later ask through the EARL commands using the same job ID. Okay, so in cases where the EARL library is running, you will be able to ask for application signature, loop signatures, and node monitoring information. And in cases where the EARL library is not running, you will be able to ask for the application basic signature. Loop signatures will not be available, and for node monitoring. So for instance, an example, so if you ask for one of the jobs with and one particular step ID, in that case the step ID 3, so that happens when you have multiple run or multiple MPI runs in a same job. Okay, you can ask for the details of each individual node with this application has been executed. With the -L is an extended information. Okay, so that case corresponds with one of the GROMACS applications used in the paper. It was a 16 nodes application, so you can see each row corresponds with one of the nodes. So you can see, for instance, the job step and step IDs, the node, the user ID, the application name, the average frequency, which could be potentially different from the selected CPU frequency. Basically, in those applications that are using extensively AVX 500 ref instructions, the execution time, the power per node, the memory bandwidth, the CPI, the energy. So for instance, when you are not asking the per node information and you ask the average for the whole application, the energy is not the average, it's the accumulated energy. And the last column, only shown with the minus L option, is the percentage of AVX 512 instructions over the total, is what we call VPI, about vector instructions per instructions, per total instructions. Okay, but it only reflects the AVX 512 instructions. Okay, because they are the ones with more weight or more impact in the frequency. So for the evaluation of the mean time to solution policy with EARL, we have selected 8 applications. 4 of them are CPU intensive cases, BT from the NAS Parallels benchmark, BQCD, GROMACS, and OpenIFS. In the paper you have all the details, and 4 memory intensive applications, POP, dances, AFIT, and suspense. Okay, so the maximum size for that applications in some cases has been 26 nodes, that it's more than 1,000 cores. Okay, and the experiment has been executed in a Lenovo system with SD530 compute nodes with 2 Skylake 6148 at 2.4 GHz 20 core nodes, that is 40 cores per node. Okay, some of them executed with EDR network and some of others with the OPA. So some of the use cases has been provided in the context of a collaboration with the SORF Open Innovation Lab. And for instance, suspense is a use case provided for LRZ. It was an interesting use case because it's really communication intensive. Okay. So using the E account, we have collected, or we have first presented the execution time, average DC node power, total energy, CPI, gigabytes per second, and gigaflops per watt. That is a metric that reflects the energy efficiency of the application. And for the evaluation, we presented the time variation, which corresponds with performance penalty, power variation and energy variation, that are energy and power savings, and the gigaflops per watt variation, and the average frequency. When in cases that we presented variation, it means the results executed at the maximum frequency 2.4 compares with the results reported by the mean time to solution, or with the mean time to solution policy. In the paper, of course, there are results for the 8 applications, but I have selected here just 2 CPU intensive use cases and 2 memory intensive use cases. So since the target of mean time to solution is to accelerate the application up to the maximum, it's an energy policy that is not targeting energy saving. It's targeting energy saving only for memory intensive applications, because applications will run at lower frequencies than the nominal. Okay, but there is an interesting effect that we show here with the GROMACS. So the BQCD application is a traditional CPU intensive application, at least the use case we have executed. So we can see some energy savings, but they are of course not relevant. Okay, but if you look in the case of GROMACS, as I presented, has a significant percentage of AVX 512 instructions. So the EARL library is able to identify that, and in that case it adapts the average, it adapts the CPU frequency to do an efficient utilization of the hardware. Okay, reporting a 10% of energy saving, which is really relevant. Okay. Concerning memory intensive applications, POP is a very good use case for us because it's a very traditional memory intensive with a high CPI. And we decided to present also suspense because it's the case I have commented, it's highly communication intensive. So it was initially a very bad use case for us because, as I said, the overhead, the main source of overhead for EARL comes from the number of MPI calls per second. So using the denies at the beginning and the overhead control that we have, we can provide an overhead under control. So as we can see here, in that case, we present results for the applications. The main comment, or the main relevant comment, is that for the CPU intensive, which are the applications in the left side, the frequency selected corresponds with the expected one depending on the let's say the amount of CPU intensiveness of the applications. For instance, OpenIFS is not so CPU intensive as the others, and the case of GROMACS, as I commented, is really special because even though it's a CPU intensive application, it uses a lot FBA by 512 instructions, so it's not efficient to run at the maximum frequency. And in the 4 applications in the right side, the default the selected frequency has been really close to the default one. In all the cases, we have provided benefits or significant benefits in the increments in gigaflop per watt being in average between 9 and 10%. As conclusions, so EARL is it's not only a runtime, even though we have focused in the EARL library in that paper. The main difference with other runtime is the coordination or the cooperation with the whole energy systems, covering all the aspects of the energy management. Okay, energy management, monitoring, control, everything. Okay, so when not using the optimization, just evaluating the overhead and not presented in the paper, we have measured less than 1% of overhead, even though in the more communication intensive applications we have been able to execute. In average, we have presented between 9 and 10%, more close than 10%, in fact, in the increment of the average gigaflops per watt. And the next versions of EARL will include new EARL library versions providing support for non-MPI applications, and also new strategies like global frequency selections for energy optimization. We will provide also integrated power cap, integrated in all the levels, EARL daemons, providing power cap in the node level. The library will be aware of that power capping and at the cluster level, and we will also provide GPU application monitoring and optimization. And that's all. Thank you very much for your attention.